Hello, I'm Ilhong. I'm an archaeologist based at Seoul National University in South Korea. And today I would like to introduce some of the results of a research project that I have been undertaking along with Dr. Woojin Shim and Professor SooJin Park, both of whom are geographers, also based at Seoul National University. And we're going to talk about, and I hope to talk about, our work on developing a multi-evidence-based pathfinding algorithm for the reconstruction of ancient pathways in ancient Korea. Okay. So the study of ancient pathways, I suppose, begins with the very basic question, which is how do we connect 2 points within the landscape? Well, if we look at previous studies, one way would be to get information from historic maps, or another way would be to refer to the archaeological evidence, such as the actual remains of ancient roads. Or it is also possible to go on site and actually walk about. And finally, there is computer modeling. And in our case, we have been focusing on the computer modeling approach. So, of course, there have been many studies which have been undertaken on the computer modeling of ancient pathways. But what sets our research apart is the fact that we have been very fortunate enough to have access to a massive data set comprising the geospatial data of 148,000 or so excavated sites in South Korea. Which was obtained from the Cultural Heritage Administration of South Korea whilst we were doing another project, but we have permission to use this data for other research purposes. And now, in the case of this data, because the sites have actually been dug, we know their functions and we know the time periods to which they belong. So what we have been able to do is to reclassify the point data according to period. And in the case of multi-period sites, a single site is represented by multiple points. So what the data we have is like this, as you can see in the table. The sites spread out from the Paleolithic to all the way up into the historic period, and it is quite a massive data set. Now, and expressed as distribution maps, the data, the points would look like this. Now, because we already had this big data, one of our key concerns was not just to model paths between one point to another, but to come up with a method of creating pathways between all of these points. So then how did we begin? So as many of you will probably be aware of, the computer modeling of pathways between 2 points generally involves the calculation of the least cost path between 2 points. This is an approach that has frequently been used since the mid-1990s. Now, in order to calculate the least cost paths, first what one has to do is to define the cost surface, which determines the cost along the cost of crossing the grid cells of the surface. Now, a review of the literature will show that slope-based hiking functions have often been used as the primary cost factor in these modeling approaches. And in addition to this, some other factors that have been used include vegetation or soil type, visibility. Now, in the case of our study, what we have tried to do is utilize hill slope position classification as a cost factor. Now, as you can see here in this table summarizing some of the literature on the modeling of least cost paths, hill slope position classification has yet to be utilized as a cost factor. And this is why this is a significant aspect of our research. So I suppose I should begin by explaining what hill slope position classification is and why its use in the modeling of pathways is significant. Well, in geography, there have been various attempts to classify the different positions of a hill slope, so as you can see here in this figure. Now, in our case, what we did was we classified the hill slope into 10 different units and designated for each unit different costs of movement according to the hill slope position. And we designated these costs based on various lines of evidence. So for example, it was possible to establish that prior to modernization, in the case of mountainous regions, pathways were mainly formed along the valleys, which according to the hill slope position classification, which would have been the toe slope. And so, for example, we designated a very low cost to toe slopes. And also we distinguish between mountainous regions and flatland and low-lying hill regions in designating the costs for each hill slope position unit. So this is what we did. And then I suppose you could ask, so what is the significance of such an approach? Well, what we would argue is that we think that this way of categorizing the landscape provides a way of approaching movement within the landscape in terms of affordances. Now, according to a recently published book on this issue of ancient pathways, what is important in determining how people move within the landscape is the affordances that the landscape gives them. And we believe that the different hill slope position units featured different potentials for facilitating human actions and movements. And that is how they can link with this topic, this issue of affordances. So now, so I suppose the characteristic, so what we did was, what we tried to do was to create a cost surface based on the hill slope position classification. But this wasn't the only thing that we did, because we wanted to compare the reliability of that with the traditional ways of using cost surfaces based on slopes. So what we did was, first we created 3 different types of cost surfaces, which would later be used to estimate the least cost path between the 2 points. And here I've brought these 3 maps. So this first map is a cost surface that is based on slope, so the traditional kind of cost surface. The second kind is the cost surface based on hill slope position classification. And the third, what we try to do is we try to kind of combine the 2. So we added the cost, so 50% from the slope based, and then 50% from the hill slope position classification based cost surface, and made this third version. And we did actually manage to test the reliability of using these different cost surfaces. And I shall share with you the results of this later on. But before I go on to do that, what I want to do is address another aspect of our research modeling ancient pathways that also, again, differs from previous approaches. And this is, the need for a more efficient way of calculating the least cost paths. So once you have created a surface map, the next step that one has to do is to calculate the costs of crossing that surface in order to identify the least cost path. Now, generally, archaeologists work only with 2 points in the beginning, the starting point and the end point. But as I mentioned, we had a lot of points at hand. So we thought it would be a good idea to come up with a more efficient way of calculating the least cost paths that could connect all of these points. So our strategy was to make in advance a node link base map of all of the least cost path connecting all of these points. But we soon came to realize that not only was this a horribly time-consuming endeavor, it was meaningless in some cases to draw direct links between 2 points, particularly if they were located far away, since pathways tend to be a chain of links between nodes rather than a single link. So at first, what we had hoped to do was, if you think of these as points, as sites, we wanted to connect all of them using the least cost path. But then we realized, for example, if you were to go from here to here, you would not directly pass through that. You would usually go via you would be connected to a key node, and then from here, go via a different link to a different link, and then make your way to your final destination. So we had to address this issue. So what the solution that we have come upon, which we are at the very preliminary stages of at this point, is first what we did was of all of the point data that we had, we selected only the settlement sites and the production sites for each period because we thought that gave us more manageable data set. And then secondly, what we did was for each watershed, we established a central node site. And we selected this watershed as a meaningful unit of space because we know from previous research that watersheds generally coincide with archaeological meaningful spatial units. And then what we did was first we calculated the least cost paths between the central nodes. And then we calculated the least cost paths between the central node and the remaining sites for each watershed. And this is how we created our least node link base map of the least cost paths. And as I mentioned earlier, because we had 3 different types of cost surfaces, we ended up creating 3 different types of node link base maps. So as you can see here to your left, this one would be the node link base map of the least cost paths, which was estimated using the slope-based cost surface. The second is the same, but which was estimated using the hillside position classification based cost surface. And then the third is the least node link base map using a combination of the 2 cost surfaces. And in terms of this, because this part of our research is still in its early stages, we've not yet tested the reliability of using these node link base maps yet. And so we hope to do that in the future and possibly give another presentation on that aspect of our research. But today, what I can show you is the results of the testing that we have done on the reliability of the 3 different cost surfaces. Now, what we did was, in this case, we calculated the least cost paths in the traditional way, so not using the node link base map. And we compared our modeled paths with known paths, which are the 3 main roads of the Joseon dynasty. So these are the 10 main roads that connected the Joseon dynasty, and we know where they passed. So what we did was we selected these points, the beginning and end points of all of these 10 main roads. And then we modeled paths using both the hillside position classification-based cost surface and the slope-based cost surface. And as you can see here, there are slight differences in terms of the total lengths of the paths and also in terms of altitude. But overall, they do tend to generally coincide. And now if we look at it a bit more in detail, so if you can see here, the black points represent, the black points represent the areas where the paths of the Joseon 10 main roads and our modeled paths did not coincide. And the left, the left is the one that was modeled using the hillside position classification cost surface, and the right one was the one using the slope cost surface. Excuse me. Now, if you compare this, what's really interesting is that in terms of the mountainous regions, the routes that were modeled using our new type of cost surface tended to coincide, show a very high degree of, they were very, very similar. So the difference was only 9% in terms of the mountainous regions. But if you look at the plains and the low-lying regions, the difference was 91%. So you can see they didn't match very well. And if you look at the pathways that were modeled using the traditional kinds of cost surfaces, they fitted better for the plains and the low-lying hillsides, but not so for the mountainous regions. And if we look at this in terms of on top of the on top of the maps, you can see that. So this is the flat landscape, and the black lines represent the actual chosen 10 roads. And the two different lines represent the modeled roads, and they do not fit very well in many areas. But if you look at the mountains landscapes, you can tell that they do fit quite well. So then what are the implications of our research? Well, the need to find a way to utilize the big data set comprising all the excavated sites in South Korea in modeling ancient pathways has resulted in an approach in which the excavated sites, which are obviously the places of social and political and economic significance for humans within the natural landscape, play a central role in the creation of least cost paths as nodes and subnodes within the node-linked base map of least cost paths. And what this does is this provides a way of integrating social, political, and economic factors when modeling ancient pathways. Now, as I mentioned, this research is still in its very early stages, and there are things that we have to do in the future. And one thing, obviously, is to develop a more efficient way of creating the node-linked base map for the least cost paths. So what we're trying to do is maybe develop ways to automatically establish what the main nodes are, because right now, I've been the one who, as an archaeologist, has going into the QGIS platform and selecting what the main nodes are. And that has been very, very inefficient. And I suppose we also have to explore how to best connect the subnodes within each watershed, because right now we've just connected the subnodes to the main roads and main nodes, and we've not connected the subnodes to each other. And so we should also explore other ways of connecting the watersheds, because right now they're just connected by connecting the main nodes of each watershed, but there must be other ways to do this. And so that's what we hope to explore in the future. So I would like to acknowledge that the data for research came from the Cultural Heritage Administration of South Korea, and that the funding for this research came from these various funding bodies. So thank you very much for listening in on my talk. And also I would like to thank the CAA organizers for giving me an opportunity to share our research with the wider archaeological community. Thank you.